Okay, so we're going to be talking about section 2.4, imaginary and complex numbers, how to graph complex numbers, and then finding the magnitude of complex numbers. None of this is that difficult. If you can remember the Pythagorean theorem, that's about as complicated as it gets. Okay, imaginary numbers are defined in terms of the letter I, which is equal to the square root of -1. You've probably seen this before. This means that we have the ability now to take the square root of negative numbers. Now remember, when you're taking the square root, you're still getting the positive or negative, but the square root of -25 can now be wrought. It actually exists as an imaginary number. Now what this means is we take the square root, so we get plus or minus 5, because that's what the square root of 25 is, but then the square root of -1, which is equal to I, becomes that, right? So what that means is we get these two answers. So it turns out when we have solutions, we end up with pairs of them. That's going to be very important a little bit later. Now, imaginary numbers, we can, and this is an interesting factoid, that would be the square root of -1 squared, which is, so it turns out if we take an imaginary number times an imaginary number, like 3i times 2i, we get 6i squared, which is 6 times -1, which is equal to -6. So it turns out if we take two imaginary numbers, multiply them by each other, we get a real number. Imaginary times imaginary equals real. Spooky, eh? Okay, this leads us to complex numbers. So complex numbers are of the form a plus bi, typically written as a group, thus parentheses, though they do not have to be, where we have an imaginary part, and that's the I. So B represents the imaginary part, so the BI represents the imaginary part, and B is an element of the real numbers. But because it's multiplied by I, it's actually an imaginary number, all told, right? So this whole thing is an imaginary number. A is the real number part. Remember, real numbers are all those numbers that we know, positive, negative, decimals, the whole shebang. Now, complex numbers, as a rule, when we'll look at what the operations are there, but they contain some sort of real number and some sort of imaginary part. Turns out that if we're looking at number systems, and I'm going to Venn diagram you here in just a sec, if we were to look at number systems, it turns out the complex numbers, now the complex numbers are denoted, there we go, by this C with this extra kind of line, right? That's complex numbers. The real numbers are denoted by the R with the extra line, like I did here. The imaginary numbers are not actually with an I. I lied. Oh no, they are imaginary. No, I'm sorry, I didn't lie. Turns out they are with this. So imaginary numbers are with this I with an extra bar. And then there's things like integers. Now we have a tie. So integers, and the only reason I mention this is someone might do this to you, integers are denoted with a Z with an extra line. So when we're looking at this, we have the complex numbers which encapsulate everything. Now within that, there are the real numbers, right? And there are also the imaginary numbers. Now it's probably the case that I should probably, now, because complex numbers are actually the sum of these two, there actually is no space out here. That's kind of a misnomer. And then within the real numbers are things called the integers. Remember, integers can be positive or negative, include 0, but they don't include any decimal portions. So just so you have some sense of the relationship, complex numbers cover everything. By the way, what this does mean is if I'm looking at the number 3, which we commonly think of as a real number, that can also be written as 3 plus 0i. That would be written as a complex number, just has no imaginary part. Likewise, if I'm looking at an imaginary number, that could be written as 0 plus 2i, also a complex number, right? I'll follow my own strictures here. It just happens to have no real part. Okay. Now, sometimes you might be asked to graph complex numbers. When you're asked to graph complex numbers, we are going to be putting the real part on the x-axis and the imaginary part on the y-axis. So if we have some number a plus bi, right, the a would go on the real number portion and the b would go on the imaginary portion. So assuming they're both positive, if we graphed it, it would be this point here, okay? So as an example, if I wanted to graph 2 minus I, right? 2 minus I, remember, real, imaginary, I would want to go 2 units in the real direction, positive, which would be right here. And then I'd want to go negative 1, I, so 1 in the negative, so this would be 2, this would be negative 1 in the imaginary. So imaginary is y, is x. So you can think of this kind of like the point 2, negative 1, just graphed on the complex plane, which means that when we graphed it, it would look like this, okay? The reason we talk about graphing is because we want to talk about the magnitude of a complex number. So it turns out that the magnitude of a complex number is defined as, okay, a squared plus b squared, okay? So this is, if you look at this, if you think about this graphically, we're talking about some complex number where we have a in the real and then b in the imaginary. So we've got this, and all this is, if you think about this as a vector, or if we extend a line from the origin, then we've got a triangle, right? We've got a triangle such that one side is b, and it's a right triangle, of course. The other side is a, so a in this and b in this. Then this is, the magnitude of this thing is a squared plus b squared, okay? Very related to the Pythagorean theorem, right? And that, as they say, is that.